Last lecture, I started to talk about electromagnetic induction. We basically said that, if the magnetic field is changing, then it will create the electric field. And then we basically really derived that the emotional, we described the three experiments that Faraday performed. First case is keep the electric field the same, but moving the circuit out of the B field. The second situation is really we keep the circuit still, but we move the magnetic field. And then the third one is really we keep the magnetic field and also the circuit the same, but we only change the value of this magnetic field. So what happened is we found that for all three cases, so there are currents that are produced in the circuit. And as we said, if there is a current produced, and we described that for the second case and also the third case is really due to a new electrical field that is induced. And because there are current flowing through the circuit, and we will have this electromotive force, and that electromotive force is really the induced field, electric field, times dl, which is really the voltage difference as we described before. And we also said that this is really equivalent to the rate change of this magnetic flux. Okay, so that is what we have, from the Faraday's experiment. Okay, and we know that this phi is really B times A. Okay, so what we really have, it becomes this partial B over partial T dot dA. Okay, this is how to calculate the magnetic flux. And from there, we see that we can write down this using the Stokes theorem. Okay, and we can write del cross E times dA. And from there, we get the conclusion is this. Okay, which is really Faraday's law. It's really saying that if the B field is changing, okay, it will create induced electrical field. Okay, so this is a very important discovery actually. Okay, and it allows us that changing the magnetic field to create current. Okay, and then we also said that for this case, del cross E is not zero. It really means this induced electrical field is not a conservative field, because otherwise, if it's a conservative field, del cross E should equals to zero. Okay, so that is what we have, to calculate, to figure out how this B is related to E. And then we also talk about how to use this Lenz's law to really find the directions of the induced current, inside a circuit. And that law really says that nature acts to oppose a change in the magnetic flux. Okay, and we can just use this simple law to figure out how to find the direction of the induced current in the loop. Okay, so now we wanted to talk slightly more about this induced electric field. So let us consider a pure Faraday field. We really means, we consider this, we just consider this, okay. Consider rho is equals to zero. There are no stationary charge there. Okay, so what we have is del dot E as a divergence is still equals to 0. Okay, otherwise it should be rho divided by epsilon 0. And because rho is 0, so del dot E is really equals to 0. And del cross E, okay, from the Faraday's law, we have this one equals to partial B over partial T. Okay. Okay, and then we said this is the induced electrical field that is caused by the changing the magnetic field B. Okay, so we need really to solve these two equations to really figure out what are the values and what are the directions of this electrical field. Okay. So these are equations that are often not that easy to solve, but what we can do is we really can look at the formula that we described before for the magnetic field. Okay, for the magnetic field, the one that we learned from this magnetostatics static, where we have del dot B is equals to 0, we have del cross B is really equals to mu 0 J. Okay, so this is what we have from magnetostatic. Static. Okay, from there, if we now you look at these four equations, and you will find that they are very similar to each other. Okay, so you see that this side is 0. This side, in principle, we just need to replace this mu 0 J with this minus partial B over partial T. Okay, but otherwise, they are the same. Okay, so in other words, that how to figure out this induced electrical field, we can use whatever formula that we derived from this magnetostatics, and we just apply the same equation, okay, for same formula, and we can find out the what happened for this induced electrical field. Okay, so that is something that is really really interesting. For example, remember that to figure out this B, we have this Biot-Savart's law. Okay, and so what we can do is we can just write it down exactly the same way. We can write down this E. Okay, we just really replace. Remember this Biot-Savart's law is really. Let me write it down. That is first 4 pi, and then we have this J cross this separation vector, okay, direction, and times d tau. Okay, so this is the solution that we have for the magnetic field that I calculated from this magnetostatics. Okay, so now what we do is we do exactly the same thing, because the equations are the same, except we just need to replace this mu 0 J with this minus partial B over partial T. Okay, so that really means we have, because there is a minus sign here, mu 0 and J will be replaced by this partial B over partial T. Cross this direction, the distance square, and then d tau. Okay, so that is what we have. Okay, and because these are the directions, okay, it only depends on the position, and this one depends on the derivative with respect to t. Okay, we basically can put this t outside. Okay, so we can, inside this integral, we just have this. Okay, so this is how we can calculate, using whatever we learned, okay, from this magnetostatic, and we can figure out the vector, for the induced electric field due to the changing of the magnetic field. Okay. And as we mentioned before, it's often not really easy to use this equation to calculate the B field and also calculate the electric field and also calculate B field, because this involved the vector cross product. Okay, and we mentioned that sometimes if there are symmetries permits, we can use this Ampere's law. Okay, for the Ampere's law, we have this B dot dl is really equals to mu zero times the current that are enclosed inside. Okay, so what we can do is we can also write down the Faraday's law. Okay, so this is the Faraday's law. Okay, it's in this differential format. We can also, using the same reasoning, we can really write down the Faraday's law in integral format. Okay, so this one really, if you see that, so this is really this mu zero times the integral of this j. Okay, because the current is really just the integral of this j. So what happened is this one will be just the integral of the this part b times the surface surface element. Okay, and then we do the integral, which is really d phi over dt. Okay, which is really, this is really the magnetic flux. Okay, I mean, you can see that this is exactly, what I already mentioned here is really this equation. Okay, but you can also look at by looking at analogy between these four equations, and you can also derive it this way. Okay. Okay, and you can see also from here. So when we calculate this, we said that this B field will be depends on the amount of current, okay, that are inside this Amperian loop. Okay, we define a loop, and we found what is the current that are inside that loop. Okay, so here in some sense is a very similar way. Is really we define some field, and we calculate how much of the magnetic flux, okay, that are passed through this loop. Okay, and we need to figure out what is the rate change, okay, for the magnetic flux, inside that loop. Okay, so you can see that they are very similar to each other. Okay, now once we have this equation, we can just show you one simple example about this. Okay, so let us say I have a loop, a wheel. Okay, so this wheel is there's some supporting structure, and then make it hang up, according on a ceiling, and okay, and this wheel has a radius. Let us say is b. Okay. Now let us say we define another area inside. Okay, this is just an area. Okay, with a radius that is a. Okay, and their magnetic field. Okay, let me use the red color. Their magnetic field B, okay, that's pointing along the z direction, okay. And there are also some line charges, okay, with line charge of density, that is lambda, okay, that is on this wheel, okay. And as I said, it is hang up there, and if there are some force applied, and this wheel can do the rotation, in this horizontal plane, okay. So now there is a magnetic field applied, only inside this inner region, okay. Now let us say if we suddenly turn off the B field, and we wanted to figure out how this wheel will rotate, okay. Okay, so what do we have? We can analyze this. Okay, so now if we look at this wheel, okay, you can think about it as a loop. Okay, so originally inside there is a magnetic flux that is B times pi a square. The area. Okay. So this is the original phi, okay. And now if we suddenly turn off, then this phi, becomes 0, okay. And as we said that the varying the magnetic field will create current, okay. So this current, will move inside this wire, okay. Okay, now we want to first find out the direction, okay, how this wheel will rotate, okay. So now remember we wanted to use this Lenz's law, really nature really acts to oppose a change in the flux, okay. So the B is originally positive along the Z direction, and then it suddenly becomes 0, okay. So using the Lenz's law, is really said that the electric field should produce a B field, that pointing along the plus Z direction, okay, in order to, oppose that change, okay. So to create, okay, so to create, another field, okay. So we will have current, okay, that will flow along this wire, okay, and then it needed to create a magnetic field that is also pointing along the positive Z direction. So in order to do that, the current, the electric field, okay, should be this counterclockwise way, okay, because if you use the right hand rule, and you can figure out that the current should really pointing up, okay. Okay, so now really, so this is what we have. So now really to figure out what is the value of this electric field, so what we can do is we use this Faraday's law. This E dot dl is really equals to minus d phi over dt, okay. And this E, we know that because of the symmetry reasons, okay. So the E should be the same, okay, for every point on the wheel, and then the length is really 2 pi b, okay. And this rate phi is really maximum value is pi a square, b times pi a square, then suddenly it becomes 0, okay. So there is of course it will not directly go from a value non-zero to 0, so there is a rate change there, okay. B, it takes time, still for B to go from some value to 0, okay. There are some rate changes there, okay. So from here you can see that the E is really equals to minus a square divided by 2b and db over dt, okay. And we also find the direction, as I said, it should be anti-clockwise way. Okay, so it should really pointing along this phi head direction. Okay, so this is the electrical field that are created. Okay, so now we said that we can look at the torque. We can look at a small amount of charge, that is lambda dl. Okay, and we wanted to count what is the torque applied on this small element. Okay, this is really r cross f. Okay, r cross f. Okay, because r is pointing afterward, and f is really just qe, a lambda times e. Okay, so it's pointing along this phi head direction. Okay, so then you can see that this torque direction is really also pointing to the positive z direction. Okay, so this one is really the radius, of course, is b. Okay, f is really lambda times e. Okay, and then times the charge is really lambda dl. Okay, so we are talking about a small segment of length. Okay, so this is what we have. Okay, so then the overall torque, okay, of course, is just the integration of this dl. Okay, so now we have b lambda, and this e value is a squared divided by 2b. Okay, and this is db over dt, and then the integral of the length. Okay, and of course this integral will give us 2 pi b. So if we add together, is minus b lambda pi a squared db over dt. Okay, so this is what happened. This is the overall torque. Okay, and of course this overall torque applied, will make the wheel will rotate. Okay, and we can find out what is the angular momentum. Okay, that we have for this wheel. So that one, we just need to do the integral. Okay, because it take a short time for the magnetic field to be reduced to zero. Okay, so if you do this integral, you basically just this one integrate. So this is b lambda pi a square. We just integrate. Originally is b0, and then at the end it becomes 0. Okay, so that is what we have. Okay, so this integral, okay, dt cancels, so this one give us minus b0. Okay, so at the end we have really lambda pi a square b0. Okay, so this is really the angular momentum that this wheel will have, because it will start to rotate. Okay, so it has angular momentum. Okay, and you can also see from here, this value you can see from here. Lambda is fixed, pi of course is constant, a and b and also b0, they are all constants. Okay, so you can see that it doesn't depend on the rate change, dB over dt. Okay, so if we slowly turn off the magnetic field to 0, or we very quickly change the magnetic field to 0. Okay, so it doesn't really affect the total angular momentum that this wheel has, because there are this changing the B field that caused the induced electrical field, and this electrical field applied on this charge and will make this wheel rotate, and then gained angular momentum. Okay, so here just shows you that this one tells you no matter how fast you change the magnetic field, at the end, the total amount of angular momentum of this wheel doesn't change. Okay, so that is also a very interesting for things. Now I wanted to talk about a new concept. It's called inductance. Okay, so this is a very similar to what we had for capacitors. For the capacitors, we kind of say that, let us take this parallel plate capacitor. We have a plus charge here, minus charge here. There are some distance, between the two plates. Okay, and then we can calculate, the capacitance. And we also said that this capacitance is a totally a geometrical effect. It depends on the area of the two plates, the distance, and also the material, that we often put between the two plates. Okay, so that is what we call it, capacitance. Okay, so now we're talking about this. There is a very similar concepts of this. Okay, in this magnetostatics. That is kind of the inductance. Okay, so what happened is, let us say I have two loops. Okay, this is my loop 1. Okay, then I have another loop. Okay, that is loop 2. Okay, so they are really not connected to each other at all. Okay, they are separated from each other. Okay, now let us say I have the current I1 that are going, around on this loop 1, and we know that it will create a current. Okay, it will create the magnetic field. Okay, let us call it B1. Okay, and we can use this Saviot's law. Okay, this is Biot-Saviot's law to calculate the magnetic field. Okay, that I introduced here. Let us consider a small line of charge dl1 here. We consider a small length dl2 here, let us say. Okay, so this is the separation vector. Okay, so now, if we look at a line charge here, and we can calculate what is the B field here. Okay, so the B field here is really, at this point, at this particular point, is really mu0 times I1, and then the integral of dl1. Okay, so this dl2 doesn't matter right now because we only calculate the B field at this particular point. Okay, times this separation vector direction. Okay, so that is what we have. Okay, and we also calculated the vector potential. Okay, which is mu0 divided by 4 pi. This is you can see from magnetostatics. So we also have this vector potential that look like that. Okay, so this is just a loop 1 that will create some magnetic field at a distance that is recursive r, away from this point. Okay, now if we want to calculate the overall magnetic flux for loop 2, okay, so this is for loop 2. Okay, you can see that for each point, I know the field value. Okay, B field value. In principle, I just needed to do a surface integral. Okay, of course, this is the magnetic field caused by loop 1, on the surface of loop 2, okay? And then we just integrate all the area for this loop 2, okay? So that is what we have. Okay, so what you can see that because B1 is really proportional to the current I1, so you can imagine that this integral should be proportional to I1, okay? And this value, I currently call it M12. So this is called mutual inductance of the two loops. Okay, it's proportional to the current that in loop 1, and then multiply by some number. Okay, M21. Okay, so there is a very nice way really to write down this M21. That really uses some tricks about this vector potential, and also uses the Stokes theorem. Okay, so the idea is really, is B, we know that is del cross A. Okay, because that is the definition. Okay, now once we do this, we can really use the Stokes theorem. We convert the surface integral to the line integral. Okay, you can see that. So the first one is just the definition of this vector product, and then from here to here we used this Stokes theorem. Okay, so this is what we have. And here I already showed you how to calculate A1. Okay, so then we can just plug it together, plug in. So the 4 pi. So what happened is now we first do this integral. Okay, now we have two integrals. Okay, so the first one is this integral, and the second one is this integral. If you think about this, because this one already have one integral on D1, so this one is another integral on D2. Okay, so this one can be written as this. There are two line integrals. Okay. So the reason there are two line integrals because we have dl1 and dl2 here, for each of the loop. Okay, so this is what happened. So you can see that from here you can see that M21. Okay, because M21 is defined this way, and this phi 2 is also calculated this way. So we just get rid of this I1 here. So we have M21 is really just this integral. Okay, so this is also called the Newman formula. Okay, to calculate the mutual inductance, of the two loops. Okay, and if you look at this formula, okay, you will see that these are really purely geometrical quantity. Okay. Okay, because this DL1, DL2, and this separation vector is really just depends on the geometries of these two loops. Okay, it doesn't depend on whatever current that are running on these two loops. Okay, and so here is how we calculate phi 2. Okay, that are due to the current on the loop 1. You can imagine that the same thing, we can make some current on the loop 2, and we calculate what is the magnetic flux on the loop 1. Okay, from there, of course, we can define phi 1 is really due to the second loop that created a magnetic flux on the first loop. So then, of course, it depends on the current, on the second loop. Okay, so here we have M12. Okay, so you can imagine, you can do the calculation, but you can very easily see that M12 should really equals to M21. Okay, because it also only depends on the geometries, of the two loops. Okay, and because they often don't really 1, 2, and 2, 1 really the same, we sometimes just use M. Okay, to indicate the mutual inductance of the two loops. Okay, we don't really need to write down the low indices. Okay. Okay. So this is just something to point out. And I also want to point out another thing is, here you can see that, let me write it down, phi 2 in some sense is Mi2, I1, okay, because it depends on the current from the first loop, it's really Mi2. Okay, so this is what we have, because M12 is equals to M21. Okay, so now you can see that the flux through the loop 2, okay, if we run a current I, okay, on loop 1, if I1 and I2 are the same, okay, no matter, the flux through 2 due to 1, and the flux through 1 due to 2, okay, they are the same, okay, if we have the same current, okay, in either of these two loops, okay. You can also see that if we vary the current, okay, through loop 1, okay, so if we vary, so if this one has a PT dependence, okay, so if this I1 depends on PT, okay, depends on time, okay, depends on time. So you can see that if it depends on time, then really means the flux also depends on time, okay. And as we said that the flux changes, it will really induce an electric field, in this loop 2, okay. And this electric field, is really a electromotive force, okay. And we really have the induced, this EMF is really minus d phi 2 over dt, okay, which is really minus m di1 over dt, right? Okay, because I1 depends on time, so it will create a current, okay, create an electrical field, okay, in the loop, okay. So that really means if I1 is changing, and it will induce some current, okay, I2 in the loop. You can see that it is really amazing from here. You can see that I1 and I2 are not really connected at all, okay. However, if we change the current in loop 1, there will be a current flowing in loop 2. Okay, so you can see that this is kind of current. You change one, it will create current in the second loop, even though they are not connected to each other. Okay. Okay, so this is interesting things to point out. Okay, another thing is, of course, changing the current in the loop 1. You can see that it created the B field, Okay. And we can also calculate the, so now let us just write it down. So let us only consider one loop. Okay. So now if we have current, let us assume is I. So it created the B field. Okay. So now let us assume this current changes as a function of time. So that really means the B field also changes as a function of time. That really means the flux of this loop also changes as a function of time. Okay. Okay. And we can, the flux, okay, we can call it L times I. Okay. So this L is really just called self-inductance. Okay, it's a self-inductance of this loop. Sometimes people just call it the inductance. Okay, don't really say self-inductance. Okay, so now you can see that. Okay, if you have current, of course it will have the magnetic flux. Okay, through itself. Okay, and if I changes as a function of time, so it will also create this electromotive force. Okay, and this electromotive force that are induced is really equals to minus d phi over dt. Okay, and because L is a constant, it's really di over dt. Okay, and as you can see from here. Okay, so the unit of inductance, okay, is called Henry. Okay, we use H to indicate it. 1 Henry is really 1 watt second divided by per ampere. Okay, so that is how this inductance, okay, the unit is defined, is Henry. Okay, and also that this self-inductance and also this mutual inductance, okay, is always a positive number. Okay, so this is just the way we define the things. Okay, and then you can also see that the the electromotive force that is induced always opposites the change of the magnetic flux. Okay, so which is really opposites the change in current. Okay, so in some sense, is some people use this word called back EMF. Okay. Okay, it's just the EMF induced always opposes the change in current. So that is why sometimes also call it a back electromotive force. Okay. Also, so what if you look at this picture again, so it really says that whenever you try to alter the current in a while, you must fight against this back electromotive force. Okay, so if you wanted to increase the current in the wire, okay, and then this electromotive force will try to decrease it, to fight against you to increase the current. Okay, so in other words, you can see that you really needed to do some work, okay, to fight against the change. Okay, and you can also see that the inductance is, as I said, is a very interesting thing, and you can like what I said, it plays the same sort of role as does the mass in mechanical system. The larger of the value of L, it will make it harder to change the current. Okay, just like if a particle is massive, it's harder to stop it. Okay. Now I just wanted to give one final example about how to calculate the self-inductance. Okay, so now we are talking about a toroid, okay, which is really has this donut shape. Okay, it's a donut shape, but here I only in principle is really a donut shape like that. Okay, but here I only look at the cross section. Okay, just a cut. Okay, so let us say assume this cross section is really a rectangular shape. Okay, so the inner radius is A, the outer radius is B. Okay, the height is H. Okay, the number of turns, okay, has n turns there. Okay, so we wanted to calculate the self inductance. Okay, so the way to do that, because is we have really phi equals to Li, so we just need to calculate the total magnetic flux and divided by the current. Okay, so then phi of course is really the B dot dA. Okay, divided by R. Okay, so here for this toroid, okay, toroid coil. Okay, you can look at equation 5.60. It calculates the B field for you, and actually the B field inside a toroid coil, okay, is really just a constant. It's mu 0 n times I, how many turns, divided by 2 pi s. Okay, where s is really the distance, okay, from the center. Okay, and each value, s value is different, and then b value will also be different. Okay, so now we can calculate the flux through a single turn. It's really, we have the b value, we just do the integral. Okay, so this is really just b times dA. Okay, the b value is mu 0 ni times 2 pi s, and this dA, okay, the dA is really let us assume a small distance is ds here. Okay, and really the height is h, so it's something like that. Okay, so it turned out that we only needed to integrate this 1 over s times ds. Okay, so that we integrate from a to b. Okay, so that give us mu 0 ni 2 pi h log b divided by a. Okay, so that is the magnetic flux through a single turn. Okay, okay, now really the indux is really n turns. Okay, okay, then divided by the current. Okay, so what do we have? We plug in mu 0 n squared divided times hi, just cancelled. So we have 2 pi, we have 2 n's here, that's why n squared there, log b divided by a. Okay, so that is how we calculate the self-inductance for a toroid coil, that has a cross-section that is a rectangular shape and also have n turns.